We sometimes forget that this planet had a climate long before we showed up and started noticing it and then eventually affecting it. But let's be clear, the climate of this planet has always been pretty nutso. Ice ages, completely iceless ages, volcanic winters, crazy methane and ammonia atmospheres, you name it. Our climate is influenced by a whole series of cycles, some incredibly long, some lasting only a few thousand years. These cycles have been churning along for hundreds of millions of years, and in most cases they'll continue long after we are gone. A look at the history of climate change on Earth can give us some much-needed perspective on our current climate dilemma, because the surprising truth is what we're experiencing now is different than anything this planet has encountered before. So let's take a stroll down Earth's climate history lane and see if we can find some answers to a question that's been bugging me a lot lately. Just how much hot water are we in exactly? Over the past 540 million years or so, Earth's environment has experienced a few large fluctuations between two very different states: greenhouse and icehouse climates. During greenhouse periods, there's a lot more liquid water on the planet and very little, if any, ice at the poles. During icehouse conditions, the global climate is cold enough to support large sheets of ice at both the poles. The most recent transition between these phases occurred about 55 million years ago, when Earth reached thermal maximum, the peak of its last greenhouse state. Back then, there were turtles and palm trees at the poles, and the equator we can assume was pretty inhospitable. Then a long process of cooling started, ultimately resulting in an ice age that we are currently experiencing at this very moment. But of course, Earth's climate doesn't just change for no reason, so what happened? Well, one theory is that the Arctic Ocean was subject to a huge bloom of freshwater fern called Azolla, which eventually died and sank to the seafloor, taking with it a massive load of carbon, which is, of course, coming from carbon dioxide, a greenhouse gas. So with less carbon dioxide in the atmosphere, the Earth began to cool until we landed in a great big icehouse. That fern is a good example of how living things can influence the climate over long periods, because over time there's been a big give and take between oxygen, which is manufactured by plants and consumed by animals, and carbon dioxide, which is spewed out by animals and used by plants. The relative abundance of these gases has a lot to do with what the climate is like at any given time. When there's a lot of greenhouse gases like carbon dioxide and methane in the atmosphere, they trap heat to create a greenhouse effect, and when there's less CO2 and other greenhouse gases in the atmosphere, the planet cools down. But of course, when it comes to the really long-term cycles, we have to talk about that all-important climate influencer, which you could probably guess at: the sun, which can affect climate in a bunch of ways. For starters, the sun hasn't always been as bright as it is now. When the Earth was young, the sun itself was just a baby, less than 1 billion years old, and about 70% dimmer than it is today. Nowadays, the sun has some serious stability, but it still varies a bit. Fluctuations in the sun's energy export run in 11-year sunspot cycles. During periods of maximum solar activity, the sun emits about 0.1% more energy than during sunspot minimums, so not a lot. The sunspot cycle has, at best, a subtle impact on Earth temperatures. But on top of that, variations in the Earth's orbit and inclination toward the sun also cause temperature fluctuations. Over millions of years, the shape of the Earth's orbit around the sun varies from nearly circular to elliptical. This causes the distance from the Earth to the sun to vary during its orbit, and with it, the amount of solar energy we receive. This phenomenon is called orbital eccentricity, and it occurs in cycles of about 100,000 years. Right now, scientists think we're probably somewhere near the minimum of this cycle, with the distance from the sun only changing slightly in a single orbit, enough to create about a 6% difference in solar radiation throughout our orbit. But when the Earth is at the peak of this cycle, the amount of the sun's energy we receive can change as much as 30% in a year, which means crazy big fluctuations in climate. While orbit changes, so does the tilt of the Earth's axis. As it spins through space, the Earth wobbles a bit, changing its angle with respect to the sun in cycles that run about 42,000 years. So right at this moment, the Earth tilts at a 23.4 degree angle, but over the eons, that can change from as small as 22.1 degrees to as much as 24.5 degrees. The steeper the angle, the more the poles are directed toward the sun, which makes for far greater extremes as the seasons change, with the poles being way warmer in the summer and much, much colder in the winter. A lot of the changes in prehistoric climate seem to coincide with these cycles, particularly the changes in Earth's orbit. And while nothing is completely certain at this point, many experts think that these orbital cycles have had huge influences on the cycles of climate change that we find in the record of recent geologic history. So while these are the most general climate influencers that we know about today, it wasn't like this at first. Between 4.5 and 3.8 billion years ago, when the Earth was just a baby, there was no climate to speak speak of. The surface was just molten lava, and it was real hot up in here. After the atmosphere eventually cooled enough for it to rain, oceans formed and land masses appeared. At that point, the sun was way cooler, but the Earth's atmosphere, which consisted mostly of ammonia and the greenhouse gas methane, kept the planet nice and toasty. Between 2.5 billion and 500 million years ago, oxygen levels rose dramatically. Much of the life that had managed to take hold by then was anaerobic, or lived without oxygen. But thanks to the evolution and hard work of kajillions of photosynthetic algae called cyanobacteria, which started pumping out oxygen like nobody's business, the composition of the atmosphere changed to the point where a whole lot of anaerobic life couldn't deal. This oxygen boom resulted in the Great Oxygen Catastrophe, one of the most significant extinction events in Earth's history. Well, it was a catastrophe for the anaerobic bacteria in the archaea, but a nice bit of luck for us, who wouldn't happen along for another couple billion years or so. I guess it's all about perspective. There was probably a big cooling around this time too, partly because of the rise in oxygen and most of the methane being removed from the atmosphere. At the peak of this cooling period, it's thought that the average temperatures at the equator were about what they are in modern-day Antarctica. Some scientists think that the entire globe essentially froze, resulting in what they call a snowball Earth. Between 500 to 250 million years ago, the planet's core cooled down to the temperature it is today, so volcanic eruptions became rare. It's during this time that we see the Cambrian explosion, where multicellular life evolved like crazy in the oceans. Photosynthetic organisms on land churned out oxygen, but there weren't yet enough aerobic organisms to breathe it in and pump the CO2 back out, so Earth stayed pretty chilly. 250 to 65 million years ago, all that changed. By then, there were lots of critters on land, exhaling all of that CO2. Pangaea, the huge honkin' supercontinent, was also starting to break up, so more land was coming into contact with the oceans, increasing humidity and helping drive the climate into a warming period. This culminated in a time when temperatures were about 10 degrees Celsius higher than they are today, and pretty uniform all over the globe. Then, another climate change driver intervened. The reigning theory is that 65 million years ago, a 200-kilometer-wide asteroid smashed into what is now Mexico, spraying up 900 quadrillion kilograms of flaming rock into the atmosphere. This probably caused an impact winter that was likely enough to kill off all the large dinosaurs and allow mammals to kind of take over. Just 10 million years later, we began the run-up to that thermal maximum I mentioned earlier. About 55 million years ago, the planet experienced sudden warming, which sent global temperatures up 5 to 8 degrees Celsius in just 20,000 years. It didn't last very long, and what exactly caused it is a matter of debate, but the geological record shows that there was a huge infusion of carbon into the environment. One of the most popular hypotheses is that it came from methane being released from sudden melting of methane-containing ice under the seafloor and at the poles. Something happened, say undersea volcanic activity or a peak in one of the solar cycles we talked about, to melt this methane ice, and once it was unleashed into the atmosphere, we were all in Greenhouse City. Because of this little escapade, the Earth went completely ice-free, the opposite of Snowball Earth, sometimes called Greenhouse Earth or Hothouse Earth. And in addition to creating an ideal climate for warm-blooded creatures like us mammals, this also allowed for the proliferation of more plant life, including that huge bloom of Azolla freshwater fern. So levels of greenhouse gases started to tank yet again, but when the next cooling trend began, this time it was different. About 35 million years ago, glaciers started to form in Antarctica for the first time, in part because there was no Antarctica before. See, while all the cycles that we've been talking about kept churning, the continents were also sliding around on the Earth's surface until land masses appeared at the South Pole that allowed glaciation to take place. Meanwhile, other formations that didn't exist before, like the Himalayas and the Atlantic Ocean, had taken shape, which helped to amplify and circulate the cooling. And thus began a major icehouse climate. When people talk about the Ice Age, this is usually what they mean, and because there's still permanent ice to be found, we're technically still in it. But this cooling hasn't been consistent. Within this ice age, there have been small warming events interspersed with even cooler events, where average temperatures were about 5 degrees Celsius cooler than today. In fact, in the past 2.5 million years, there have probably been around 25 glaciations, or cold periods, sometimes called little ice ages, interspersed with interglacials, which are warmer periods. You might notice that that comes out to about one climate swing every 100,000 years, which coincides with that orbital pattern we talked about. And that brings us up to now, or, within about 12,000 years of now, which is like yesterday in geologic time. So you've heard of the hockey stick, right? It's this graph depicting the average global temperatures over the last 2,000 years or so, based on what can be gathered from historical data, tree rings, corals, and ice cores. You'll notice that average temperatures increased dramatically during the 20th century, which is when we started relying heavily on fossil fuels to power our everything. This graph came out in 1999 using data collected by Penn State climate scientist Michael Mann, who has taken an incredible amount of heat for this research over the past 15 years. But new research reconstructs global temperatures further back than man did, 11,300 years back, using fossilized plankton dug up by oceanographers from 70 sites worldwide. On one hand, it shows that temperatures for about 20% of this historical period were actually higher than they are today. But it also shows that right now, temperatures are increasing faster than they ever have. In the past 100 years, temperatures have risen so dramatically that they have canceled out all of the cooling that took place over the past 6,000 years. And probably more important, the study shows that in addition to being in the middle of a long-term ice age, we should now be entering the bottom of a several thousand-year-long cooling period, even if it were just natural factors. But it's not. So this new evidence pretty much corroborates what's already known, that we're making a mess. But one thing's for sure, our planet's climate has dealt with a lot, and it'll probably survive humans. But what the cost will be for us, we're gonna need some more data on that. Thanks for watching this episode of SciShow. If you have any questions, comments, or suggestions for us, you can find us on Facebook and Twitter, or down in the comments. And if you want to keep getting smarter with us here at SciShow, you can go to youtube.com/SciShow and subscribe.